you all for joining us for this November AstroTour. Today we'll be having a conversation with our old friend the Moon, but before we begin, just a few things I want to go over. As many of you know, we open up our telescopes for viewing after the talk, but today we're not in our usual room, so we'll have a guide to bring you to the other building where the telescopes are. So if you're interested in that, please stick around. For those of you who sign up for a planetarium show after the talk, our volunteer Dana in the back, who's going to wave, will take you over there. If you're in the 9 o'clock show, you need to go right to the back with Dana to go to your show. Otherwise, you meet in front of the elevators in the other building as usual. With that out of the way, I'd like to remind everyone that this event is hosted by the Graduate Astronomy Student Association at UofT. We'd like to give you all feedback forms on your way in. We'd love to hear how you did, and we'll have cookies at the front for those of you who are happy to fill them in for us. With all that said, I'd like to introduce our speaker tonight, Ari Silbert. Ari is a PhD student at the University of Toronto, and he's going to talk to us tonight about the moon. So give him a hand.
Hello, everyone. Can everyone hear me if I just talk like this? Yeah. Is this okay? I think it's a little bit easier then, so I'll refrain from this. All right. So here, as just been said, I'm here to talk to you guys tonight about the moon. So we see the moon in the sky night after night, month after month, and it's, with our busy daily lives, it's easy to take the moon for granted. But the moon is intimately connected with who we are and where we've come from. The moon has been there for all of recorded human history, like an old friend. For example, the moon has watched the building of the pyramids. Many scientists and archaeologists still wonder today exactly how the pyramids were built. And although no one here today exactly knows how the pyramids were built, the moon certainly knows. The moon is witnessed when sailors first tried to cross the Atlantic Ocean, trying to search for the new world, for glory and riches. And it watched as many of them were lost at sea before we finally made an impression and finally made it over to the other side. It's also been there during the countless rise and fall of civilizations, and it's been able to see the capabilities of humans' ability to create and destroy. And it's also been a primary driver for the advance of technology and advancement of society. Not to mention, the moon is going to be there long after we're gone, watching over humans, and even if something else happens, then it will be there for that too. More than just a passive observer, though, the moon is intimately connected with our culture as well. One of the oldest superstitions, dating back to at least 1 AD, is that during a full moon, a human, if they look at a full moon, they can turn into a werewolf. And werewolves throughout history were hunted like witches, and as a result, people were very afraid to go out during a full moon because they didn't want to be attacked or they didn't want to turn into a werewolf. In addition to werewolves, there were also lunatics, which apparently lunacy was a disease that you could catch if you were outside during a full moon. Lunacy, the root word is luna, and which is the Latin word for moon. So the moon has had a pervasive role throughout society, throughout human history. In more recent times, though, it's had a more positive and more optimistic view in different places in society. And so thankfully now we have a better view of the moon. So when I was constructing this talk, I realized there's a lot to talk about, and there's a lot of different things I could go over. And so I was unsure exactly where to start. But I decided that the best place to start is at the beginning, with the formation of the moon. Where did it all start, and how did we get to this day now? In addition to the formation of the moon, I'm also going to talk about tides, the interaction of tides on Earth and the role that the moon plays, the future of the Earth-Moon system, what's going to happen into the future, and then also the not-too-distant future of in the immediate next 50 years or so, or 100 years, what is going to be the role that the moon's going to play with humans. All right, so let's get started. So where does our journey begin when we're trying to figure out where the moon came from? Our journey starts here, not too long ago actually. In 1969, when Neil Armstrong first landed on the moon, from the perspective of America and Russia, this was a huge triumph for America, flexing its muscles. It was the superior nation to land on the moon first kind of thing. But in reality, there was an ulterior motive for the reason why we went to the moon. And that was to get some of these guys, moon rocks. It turns out that most of the things that we know about where the moon came from, the evidence that we've picked up comes from these moon rocks, which the only way we can get them is to physically go to the moon, get them, bring them home, and analyze them. So there's three main pieces of evidence that we extracted from the moon rocks. So the first one is the oxygen abundance ratio. So you might have to jog your memory to grade 11 or grade 12 chemistry. What's oxygen isotope ratios again? So it turns out that oxygen comes in a couple different flavors. So everyone's familiar with oxygen. We need it to live. We breathe it in every day. And so this is the normal one that we're used to. It has 8 protons and 8 neutrons. But there's another one, oxygen 17, which has an additional neutron. I've highlighted it in red. And as a result, it changes its chemical properties, and it's a slightly different substance. The thing that we care about, though, is the ratio of them. So if we pick up a rock and we analyze how much oxygen 17 is there relative to the amount of oxygen 16, it turns out that if we, for example, go to Mars, we sent probes to Mars, the relative abundance of these two elements is very different from that on Earth. But when we look at the moon rocks, it turns out that the relative abundance of these two species are basically the same, which is a huge clue as to where they came from, because any other celestial object, it's not guaranteed that it would be the same. In fact, it would probably be different. So that's a big clue that they're basically the same for the moon and for the Earth. The second is that there's very little and basically no volatiles on the moon. So in particular, what's a volatile? So the best example of volatiles is water. So there is some trace elements on the moon, and especially near the poles, there is some water. And this water was delivered later, after the moon was fully formed. Then we see all those impact craters on the moon, and so as a result, there is a little bit of water. But for the most part, there's no water on the moon. And so what that tells us is that it had to have been very hot in the past. Because as we all know about water, water boils at 100 degrees Celsius and it freezes at 0. And when you think about the range of temperatures that are possible in the universe, 0 to 100 is very, very narrow. So if there's no water on the moon, that means that the moon had to be very hot in the past, and it boiled off all that water, and that water escaped into space. All right, what is the final clue that we have? The final clue is that the moon has an extremely small core. So combined with the moon rocks and evidence studies that we've just done from the ground, for example, the Earth, its core is about 30% of the total size and the total mass of the Earth. But in the case of the moon, it's only 1%. It's extremely, extremely small. Most of it is this surface light material. It's very light. And so this is a huge clue as to where the moon came from. Okay, so now that we're armed with these pieces of evidence, let's go through the different theories. The origin of the moon is actually not very easy. It turns out that when people were first experimenting with different hairstyles, and when the first Nintendo system was coming out, we still didn't have a great idea as to where the moon came from. In case people can't guess, this is about the 80s, the 1980s. By the mid-1980s, we still didn't know for sure where the moon came from. And therefore, people in this room, there's probably many of you who are older than the theory of the moon, which is kind of weird to think about. Okay, so what are the main theories that we've come up with? So the first one, and this is also the oldest one, is the theory of fission. So this was invented in 1878 by George Darwin, which is the son of the famous Charles Darwin, who people know invented the natural selection and the origin of species, and he was made a very great contribution to biology. But his son, Charles Darwin, he made a contribution to astrophysics. His fission theory essentially stated that in the past, the Earth was spinning so quickly that it literally flung material off into space. To support his theory, he looked at the Pacific Ocean. There's huge gouges in the Pacific Ocean where there's just a void of material. Marianas Trench, you can see, compared to Mount Everest, is extremely, extremely deep. And so why did these gouges happen? He proposed that this used to be filled in with material, but because the Earth was spinning so fast, it literally flung material out into space. But there's two problems with this theory. Scientists have done the math, they've done the calculations, and they realized that the Earth probably would have to have been spinning much too fast for this to happen. In order to see how the required speed at which it'd have to be spinning, probably the Earth wouldn't be spinning that fast in reality. If it just formed on its own, just floating in space, it wouldn't have that kind of spinning energy. The second is that this theory doesn't necessarily require that the volatiles have to be burned away or that the water had to evaporate. So this theory is unfortunately not correct. So the second theory is the condensation theory. This theory is pretty straightforward, and scientists always like, when possible, to have the simplest theory that we can. This theory essentially stated that the moon formed where it was, and the Earth formed where it was, similar to how many other moons, or around Saturn and Jupiter, kind of just form out of the debris, and there's a circumplanetary disk. The main problem with this theory, though, is that if the moon formed where it was, in many respects, it would simply be a scaled-down version of the Earth. So, as I stated before, the Earth, its core, is about 30% the mass or the size of the full Earth. But the moon is only 1%, its core is only 1%. And so if the moon just formed on its own, its core would have to be substantially bigger. But we don't see that. So this is unfortunately ruled out. So the third theory is the giant Kittycat theory. And so this theory states that the Earth was a giant kitty cat and the moon was a giant mouse. And it was a very popular theory at the time, but it was eventually ruled out because it didn't really make sense in the end. But it was very popular. It stuck around for a long time, surprisingly. So this one is not right. Which leads us to our final theory, the giant impact theory. And this states that a long time ago there was a body, Theia, and the proto-Earth, the early Earth. And at some time in the past, they collided, there was a huge catastrophic explosion, and then as a result of that explosion, the Earth and the moon was formed. So how does this explain the evidence? So, if there was a collision and the material merged together, then whatever came out of that debris would be made of the same stuff if this was merged all together. And so, as a result, the Earth and the moon would have the same oxygen ratios. If there's a huge catastrophic explosion, then that would create very hot temperatures, and so that would probably burn away all the water, and therefore there would be very little water on the moon. And finally, if the moon, if after this explosion it sent a lot of surface material from the Earth into space instead of the core material, which is very likely to have happened, then the moon would be made of very, very light surface material. And so in general, this explains the characteristics that we see. So this is the best theory that we have today. Okay, so now I want to show you guys some simulations. This is currently still an active area of research. When you look into Google and you type in giant impact theory, there's this big Wikipedia article, and it sounds like everything's explained. We have all the answers. But this is still very much an active area of research, and there's still a lot to know. It turns out that even at the University of Toronto, there's John Dubinsky. He's one of the foremost scientists working on this problem right now. And he's been gracious enough to give me some simulations that I can show to you guys today. So here is the Earth, and here is Theia. And what I'm going to show you, we'll show them collide, and in this case, they're both about the same mass. So let's get this started, and let's walk through this. So here they are coming in, and then you see there's a huge explosion which just sends particles everywhere. And then after a while, they start to merge a little bit, and you can see that eventually they become quite homogeneous. It's hard to tell which half was the blue half and which half was the yellow half. It's all kind of the same. But there's one thing that is not showing up here, which we need, and that is a debris disk. So a debris disk is a disk like this that shoots off into space, and it's a very thin disk. And in order for the moon to form, it needs a disk of particles to kind of collect and form out of that. But here you just see particles flying everywhere. There's no cohesion to that. Okay, so now let's go to the next simulation. And oh, I think I missed one. All right, and so this looks basically the same. The only thing we're going to change is the angle at which they collide. Here you can see it's almost head on, and now it's just a little bit different. And I'm actually going to play a little bit of music, I think, if this is going to show up. It just seemed so fitting when I was making the talk. Exactly, they're dancing. So now you can see a disk is being formed in this case. A nice clear disk is being formed. All right, let's cut the music. All right, but here in this case, so now you see a disk is formed, but here you can see that they don't mix in the middle. The orange half and the blue half are still very much their own size. And so this is not what we want. We want the material to be very well mixed, but we also want a disk. Let's play this one more time, the exact same simulation, but from the side view. And so what scientists call this, the Earth and the Moon, is a very chaotic system. And what a chaotic system essentially means is that if you just change the input parameters a little bit, you can have a drastically different result. So in this case, the only thing that we changed was the angle at which they collided. The masses were the same, the compositions were the same, and now we end up with a disk, whereas before we didn't end up with a disk, and then in this case, the main body is also not well merged in this case, whereas in the original case, it was very well merged. And this is why it's so hard to know exactly how the Earth and the Moon was formed, because there's so many variables you have to think about. You know, how hot was the material, how many particles were there, what was the masses of the objects, what was the angle at which they collided at, and the list goes on. And there's so many different things you can think about, and you have to get it exactly right in order to end up with the Moon and the Earth exactly as we see them today. I'm going to show you one more simulation of a different research scientist, and you can see that the simulator looks much different than John Dubinsky's. This is by Robin Knupp at University of Boulder, and you can see that, so here we have a temperature map. John Dubinsky didn't have a temperature map, and even using a different simulator can result in different results. So this is why it's so hard to understand exactly how the Moon and the Earth formed. So there's still a lot of research that we have to do, but it's generally accepted at this point that at some point there was a collision between two bodies, and as a result of that catastrophic collision, the result was the Earth and the Moon. Okay, I now want to move into my second part of the lecture, which is tides. Here's a picture right here of the Bay of Fundy, which is in between Nova Scotia and New Brunswick. And so the Bay of Fundy has the highest tides in the world. Between its low tide and its high tide, the water can change by as much as 50 feet or 15 meters. So if you picture the Olympics and the diving boards, the highest diving board, it's even taller than that. That's only 10 meters. So it's 1.5 times that is the maximum amount of water that can change, which is a huge amount. So how does the Moon play a role? And how does this happen? And why does the Bay of Fundy have the largest tides? Okay, so I know everyone took a breath. Oh, there's math here. Okay, I'll try to work it through with you guys. It's not so bad. So everyone's familiar with gravity. If I jump up, I come back to the ground because the Earth exerts gravity on me and pulls me back down to the ground. This is the fancy equation for that describes gravity. The important part is that it's dependent upon the distance, r, which I have right here. So because the Earth is so large, it gets different pulls. It gets different gravitational pulls from different parts of the Earth based on where the Moon is. So the near side gets a very strong gravitational pull. That's why it has a long arrow. But the far side has a very weak gravitational pull because it's so far away. So it has a small arrow. So if I was going to assign a ranking scheme to how strong these forces are, 3 would be a very strong gravitational force. You can really feel that force. 2 is a medium one, and 1 is a very weak one. So if I wanted to figure out what the average force was, or the force with respect to the center, I'd subtract 2 from every number. So 3 subtract 2 is 1, 2 subtract 2 is 0, and 1 subtract 2 is -1. So -1 means that there's a repulsive force, which is kind of weird to think about. How can there be a repulsive force if there's 2 attracting bodies? I'm sure there's better analogies, but the analogy that I like to think about is, let's say if you're sitting in a car and the car suddenly accelerates very quickly, you're going to have a sensation that you're getting pulled back into your chair. Similarly, the center of the Earth is like that car accelerating forward, and then the far side is like you sitting in that chair that's going to feel this force backwards because this is accelerating very quickly and you're kind of just sitting right there or not accelerating as fast momentarily. So when we put water in the mix, the water is going to fill the container of the Earth. So, for example, if I pour water into this glass, the water is going to take the shape of the glass. So what's the shape of the Earth, or what's the shape of these forces? And it's that. This is what the shape of the Earth is under the influence of those tides. So when we put a person in the mix, then we see why we have high and low tides. And the key thing to know here is that the tides only care about where the moon is. It doesn't care about the Earth. It only cares about where the moon is, because that's what's exerting those forces. That's what's pulling the water to those different directions. And so if we start here at a high tide, then when the Earth rotates, and since we're standing on the Earth, we rotate with the Earth, but the ocean, the tides stay exactly where they are, because the tides, again, they only care about where the moon is. And the moon, after 6 hours, the moon hasn't changed anywhere. It's basically in the same spot. So as a result, if we started off and we looked outside our window and it was a high tide, then when we look again, it's going to be a low tide. And then 6 hours later, when we look again, it's another high tide. And then again, it'll be a low tide. And so for a given day, we get 2 high tides and 2 low tides over the course of a day. And that's because over the course of a day, the moon is not changing. But compounded with this, the moon is also changing over the course of a month. Everyone maybe is familiar, every month the moon goes around the Earth once. And as a result, the tides are now going to follow the moon. So let's say you had a beautiful cottage on the beach. Don't we all wish that we had that? And so let's say every day at noon, you looked outside and you looked to see if it was a high tide or a low tide. Here's us, and here's the moon, and here's the sun, and this is noontime. So then if we looked outside on day 1, it would be a high tide. Then about 7 days later, if we looked outside, it would be a low tide at noon, because the moon has moved a little bit now. And again, as I said before, the tides only care about where the moon is. So then it'd be a low tide. And then again, 7 days later, we looked outside our window, it would be high tide again. And then low tide one more time. And so as a result of where the moon is and how the Earth rotates, we end up with high tides and low tides, because the water is only following where the moon is. If there's one thing that you grasped out of that whole section, is that the tides only care where the moon is, and they follow the moon. One more thing that I just want to talk about with the tides and the physics of tides is that the sun also contributes tides. About 1/3 of the tides that we see here on Earth is as a result of the sun. So as a result, we can end up with spring tides and neap tides. So spring tides have nothing to do with springtime. It's just, I'm not even sure why they named it that, but that's the name that they give it. So when the Earth and the moon and the sun are all lined up, then we have what's called a spring tide. So this white is the forces that are exerted by the sun, and the blue is the forces exerted by the moon. So when they all line up, you get a super strong tide. But then, a little bit later, when the moon is rotated, the sun's tides are still where they are, but the moon's tides have changed. And so now they kind of cancel out a little bit. And so as a result, we have a weaker tide, and the tides overall are not as strong. If we looked at the Bay of Fundy tides would not be 50 feet anymore. They might only be 25 feet, because they're a little bit weaker because the forces are somewhat canceling out. Okay, so let's return now to the original question. Why does the Bay of Fundy have the largest tides in the world? So here's the location of the Bay of Fundy. Here it is right there, and here's my hometown, Halifax. I'm actually from Halifax. Yeah, repping the 902. Yeah, I actually haven't been home in a long time, so every time I see this picture, it gets me so deep. But anyways, we're talking about the Bay of Fundy. So why does the Bay of Fundy have the highest tides in the world? So everyone probably at some time in their life has swung on a swing, or they've been pushed on a swing. And a swing is the best example, the simplest example of what's called resonance. So let's say if I wanted to push someone on the swing, if I wanted to get them really high, I wouldn't randomly push like this, as hard as I could or as fast as I could. You have to find the right frequency, the right time to push, and you have to go nice and easy. And then all of a sudden, the person will start to gain height, and it'll go higher and higher. And so the swing has a special frequency or a special time where you have to push it at just that right time, and then it'll get higher and higher. And so the same is the case with the moon. The moon is exerting these tides on the Earth, and it turns out that the Bay of Fundy is just the right length so that it's almost like the moon is gently pushing the tides into the Bay of Fundy, similar to how you push someone on a swing. And because it's just that perfect length, then all the tides come rushing in at one point, and then they all come rushing out in the next moment. Compounded with this issue, compounded that it happens to be the right length, it's also a dead end over here. If the Bay of Fundy maybe funneled out somewhere else, then some of that water would leave and you wouldn't get such high tides. But because it's a dead end over here, the water can only go up. And so as a result, you end up, because of this resonance and because it's a dead end, you end up with extremely high tides in the Bay of Fundy. So one thing that I've been asked a couple times, can tides affect humans? Can tides affect you and I? Let's say you had dreams to be a basketball superstar one day. Could you use the moon to make yourself a little bit taller and turn yourself into one of those dunking superstars? Because after all, it bulges the Earth, so could it bulge you a little bit? So let's just recollect one more time how the tides are created. It happens because there's a difference in the gravitational force between the near side and the far side. Because the Earth is so large, this gravitational force is way stronger than the other side, and so then when we do an average subtraction, then there's a net pull in each direction. But it turns out for a human, the difference between your head and your foot and your feet are so small that there's no difference in those arrows. There's no difference in force because you're just not large enough that the moon can pull on you differently. It turns out that even for the Great Lakes, for example, let's take Lake Superior. The difference between the near side and the far side with respect to the moon is still so small that you still don't get an appreciable difference in those forces, and therefore there's no real net tide. So that's why most lakes do not have any tides. It's only the ocean that really has tides. If you constructed a really, really large lake, then you would get appreciable tides. So it turns out Lake Superior does have a small tide, maybe something like a couple centimeters. But when you also factor into the mix that there's a lot of wind and there's a lot of rain and there's a lot of other forces at play, then it's hard to distinguish, oh, was that a tide from the moon, or is that just a little ripple from the wind or something like that? And so as a result, there's no real appreciable tides. But let's say we were determined for humans to have that tide, to feel that tide. What could we do? So it turns out when we turn back to this fancy equation over here, there's three factors that affect it. So G is a constant. Don't worry about it. Just ignore it. The mass of U, this is the mass of you or the Earth or whatever object you're considering. This is the mass of the moon or that perturber, the thing that's creating these forces, which is the moon in this case, and the distance between these forces. So this would be the height of U, which isn't going to change. This would be the mass of U, which isn't going to change. This is a constant. It's not going to change. So the only thing you could really do if you wanted to feel those forces is to change the mass of that perturber. In our case, if we were determined, we'd really have to ramp it up to, say, a black hole or something like that. But if we did go near a black hole, then we would actually be able to be taller. It would stretch us out. Scientists call this spaghettification. Maybe you've heard that before. It's the same thing as tides. They're exactly the same thing, just a different terminology. So you would, for a brief moment, be able to be that absolute superstar, that NBA superstar, if you went near a black hole. But you might not survive to tell the tale, but you might. I mean, no one's ever done it, so maybe you can be the first. Okay. So now let's go into part 3 of our lecture, the future of the Earth-Moon system. So now we know how the tides are affecting Earth. So how is this going to affect it in the future? So I want to warn you guys that this next part is going to be a little bit conceptually challenging. I know everyone can get it, and I'm going to break it down, but if you're not grasping all of it, don't worry, because this is something that even a lot of scientists struggle with. But I feel like this is very essential, so I'm gonna try to go through it, and I think everyone can get it. Okay, so first I'm going to show you what the Earth and the Moon are doing, and then I'll tell you how it's happening or why it's happening. So it turns out over time, the Earth and the Moon are moving further away from each other, like that. So here's the starting position, and this is the final position. And in addition to the Moon moving further away, the rate at which the Earth turns is slowing down. So these large arrows mean it's spinning very fast, and then it's spinning slower and slower as the days go by. So this is a result of what we call angular momentum. Whoa, what's that? So we're going to break it down with a figure skater. This is the classic example for conservation of angular momentum. And so when we're watching this video, I want you to imagine that the body is the Earth, and her arms represent the moon, or the distance that the moon is away from the Earth. So she starts out, her hands are far away, and when she pulls them in, she starts spinning very quickly. Let's watch this again. Slow, and then fast right there. She quickly speeds up as she pulls her arms in. So what's happening? It turns out that this has to do because angular momentum, scientists use the letter L. I don't know why we do it, but that's what we do. And it's because the angular momentum for a given system is always constant. So the angular momentum is dependent upon R, the distance of her arms, how far they are apart, and the velocity, how fast she's spinning. And so because it always has to be a constant, I don't know why it has to be a constant. God or whoever just made it that way. I can just tell you how it works. I don't know why it works. So don't get too confused about that, because I'm just showing you how it works. So as one thing changes, as she changes her arms, then the velocity has to change as a result. So as her arms get shorter, the velocity has to get faster. Let's watch this one more time. I know you're getting sick of it. So pull her arms in, and then the velocity has to get faster. So this is happening in reverse with the Earth and the moon. So this, where we currently are, this is like the figure skater. Her arms are wrapped up tightly. The moon is very close. And so the Earth is rotating very quickly. But then, as a result of tides are actually pushing the moon out over time. Because of these tidal forces, which I just talked about in the last section, it's pushing the moon out, but because angular momentum always has to be constant, it's slowing down the Earth as a result. Because of that same figure skater concept. As the moon moves out, it's like I'm opening my arms, and then I have to slow down a little bit. It turns out that when the Earth was first formed, it's estimated that an Earth day was only 3 hours long, which is kind of crazy to think about. And when the dinosaurs roamed the Earth about 250 million years ago, then an Earth day was 23 hours instead of 24 hours, which we're used to today. And into the future, the day is going to keep getting longer. It's estimated that every year, let me make sure I get the number right. So the year is slowing down by about 2 milliseconds every 100 years. So it's very, very slow. It's very slow, but it is happening. So as a benchmark, every 250 million years, the day lengthens by about 1 hour. So it's very slow, and the moon is moving away from us at about 5 centimeters per year. Maybe it's 4. It's centimeters per year. So it's very small, but it is a noticeable amount. So we're exiting that nerd zone now. So if you've been holding your breath for a while, you can exhale, take a breath, regroup. So how does this end? How does this end? What's the future of the Earth and the moon? So it turns out that the moon, we only get to see one face of the moon. This is the face that everyone only gets to see. Maybe you didn't know that, but only a couple people in human history have actually seen the far side of the moon with their own eyes. Here's what the far side of the moon looks like this. So this is a throwback Thursday to when the Luna mission when the Russian Luna 3 probe first went to the far side and actually took a picture of it. So I have a story for you guys. So I was given this lecture last night to my dad, and at this point in the lecture, he goes, whoa, Ari, slow down. What's a throwback Thursday? And so I told him, oh, that's easy. It's a recent social media phenomenon, and it gives people an excuse to post old pictures of themselves, old selfies, old pictures, because it's a nice, cute alliteration. And since it is Thursday, then why not? And he goes, okay. Well, what's a hashtag? And I go, oh, okay, well, that kind of is also a new social media thing that we use to kind of make things more significant and more official. So for example, if I went up to someone that I really cared about and I said, I love you, if I wanted to make it even more official and even more significant, I'd say, I love you, hashtag, something like that. And then they would be, oh, whoa, that really means a big deal. So if you're not familiar with those things and you're trying to connect with the social media generation, throw in some hashtags, some Throwback Thursdays. So anyways, got a little sidetracked, but anyways, so we only get to see the near side of the moon. This is only what we get to see. So it turns out the same thing is going to happen to the Earth. Let's watch a simulation of what's going to happen. So at the beginning, the Earth is rotating like normal, and the moon is going around, but then the Earth is going to eventually slow down, and only one side of the Earth is going to face the moon. So this is a simulation taken from Minute Physics, and it's a great simulation. The only thing they got wrong is that the moon should be moving out over time, and it's not, and they didn't account for that. But otherwise, it's a great simulation. Let's watch it again. So the Earth is spinning very quickly, but then as a result of tides, the moon should move out, and the Earth is going to slow down over time. And so similar to how we only see one side of the moon will only get to see one side of the Earth. So what's going to be the consequence of this? So the first consequence of this is that only some people will get to see the moon. You can imagine that there might be some bourgeoisie society that are just bored of looking at the moon because it's just there all the time, day and night, no matter what, it's just always there. And then there'll be some poor souls that never get to enjoy the moon. It'll always just be out of their view, and if they want to see the moon, they have to travel to the bourgeoisie side to see the moon. The second is that the Earth day and the lunar month will be roughly the same, which will turn out to be about 40 days. And so as a result, we can maybe get rid of either months or days, because they'll mean the same thing. So instead of Monday, we could have January. Instead of Tuesday, we could have February, and so on. You know, you can think about how long your workday would suddenly become. It would just be unbearable. And furthermore, a single day will get very, very long. So a daytime will be 20 current days, and nighttime will also be 20 current days. And so it'll be a much different lifetime. It'd be a much different experience than we're used to. So it will have very, very hot temperatures during the day and then very, very cold temperatures at night because it'll never get to see the sun. But don't worry, because these guys have done some calculations, and they've calculated that it's only going to happen in about 1 trillion years, or maybe hundreds of billions of years. As I said, you know, per 100 years, it's only slowing down by about 2 milliseconds. Our day is lengthening by 2 milliseconds. So there's nothing really to worry about in our day-to-day, but it is something that is happening. It's kind of a relationship between the Earth and the moon that is occurring, but we don't really notice it, but they are noticing it, certainly. All right, let's go into the last part of my talk, the not-too-distant future. Where are we headed in the next 50 or 100 years with the moon? So just a brief history of our interaction with the moon. The first interactions were in 1959 with America and Russia, or the Soviet Union at the time. And they sent probes there. That was the first time. And then only in 1990 did the third country, Japan, actually send something to the moon. And then more recently, China in 2007 and India in 2008. Now I'm leaving out someone, which is the European Space Agency. So collectively, the European Space Agency, the European nations, have also contributed to this. But as far as individual nations, these are the only 5 that actually make the list right now. So from a scientific perspective, maybe something that countries could work together to build on the moon, the most obvious thing would be a space observatory. So why would this be useful? Maybe you guys have heard of that, you know, an epic moon base on the moon. But why is that actually useful? So the first reason is that there's no light pollution on the moon. So everyone is here tonight, so I'm assuming you have some general interest in astronomy. So you guys have probably looked up at one point in Toronto, and you'll notice that you can't see any stars. It's really boring. You maybe get to barely see the Big Dipper, but you don't get to see many stars. And that's because there's light here. There's so much light from the city. There's also real pollution, but because there's just so much light in general, that obscures our ability to see stars. If maybe you've ever gone camping with your family or just away from the city, you'll notice that if you look up, you can see many more stars. And if you haven't noticed that, you definitely should, because you're really missing out. There's a lot to see there away from the city. So on the moon, there's no cities. So you can see the stars much clearer. The second reason is that there's no atmosphere. it turns out that when scientists try to take observations, the atmosphere is a huge annoying part. I mean, day to day, we all would rather the atmosphere be here. But if we are purely astronomers, we would like to do away with the atmosphere because the atmosphere scatters light like you see here. And so if we want a very crisp observation of this light ray, then the atmosphere, it actually jumbles it around and shakes it around a little bit, and so you get a little bit of a distorted view. But on the moon, there's no atmosphere at all. And so as a result, that straight line would go all the way down to the moon, and you get a very crisp and clear observation. The third thing is that it's very radio quiet on the moon. So here's an image of all the interactions in a given day from Facebook. And you can see that it lights up the whole world. And so if you're trying to do radio astronomy, this is purely noise. We would like to do away with this. So think about not only Facebook, but all the other social media sites you go on, all the internet searches you make, all the television shows you watch, all the cell phone calls that you make. All of those contribute to the noise that we wish we could get away, just cut out if we are radio astronomers. And so on the moon, there's none of that as well. And by definition, on the far side of the moon, the side that we never get to see, none of these radio signals would make it there. And so it would literally be dead silent. And so it would be perfect for radio astronomy. But in addition to maybe scientific goals, inevitably there's also going to be commercial goals on the moon as well. So in 2014, Lux Space became the first corporation to actually send a probe to the moon. They sent it aboard the Chinese spacecraft in 2014. In addition, Google currently has a Lunar X Prize where they're going to award any corporation $30 million if they can successfully send a probe to the moon, a little robot that will walk around and collect some data for them. And this is currently underway. It's going to end in 2017. And corporations are currently right now trying to build that. And then there's this guy, Dennis Hope. He's been selling real estate on the moon since the 1980s. It sounds kind of funny. The story goes, in the 1980s, he was dead broke. He basically had no money. And one day he just looked at the moon and he said, no one's made a claim to this yet. I'm going to do it. So he wrote to the United Nations. He sent out to all the newspapers and he said, I hereby officially own the moon. If you have a problem with that, you can challenge me in court. And they didn't really take him too seriously. But he interpreted that as, well, I guess I own the moon now. And so he's made millions of dollars selling real estate. And to date, he sold about 7% of the moon to people. $20 an acre. You can call him up right now if you want to. And so, although this will probably, when the time comes to really start colonizing the moon, he probably won't be able to fight the big giants because really I wouldn't take him too seriously, even though he's made a lot of money from it. But the fact of the matter is that these are issues that we're going to have to address in the future. Let's say every corporation on the Earth wanted to land on the moon. There's not enough space for them. So who gets to land there? Who gets to decide who gets to land there? Who has the rights to the moon? Right now, it's kind of just open to everyone because we don't have to worry about it. No one, I can't go, you can't go. There's no reason to really define these boundaries. But in our lifetime, as people and corporations really start getting going to landing on the moon, that's something we'll really have to think about. Not to mention, there's all these amusement attractions you can think about going to the moon. Raise your hand if you'd love to go to the moon. Exactly, I'd love to too. So here's a video of some astronauts jumping around on the moon. So one of the greatest things is that the moon has very, very low gravity. It has about 1/6 of the gravity that's here on Earth. And so as a result, you can jump about 6 to 10 times higher on the moon than you can here. So going back to that superstar NBA player, if you wanted to be able to dunk, instead of trying to use the moon or go to a black hole, you could just go to the moon and you'd easily be able to dunk. No problem. It'd be easy. Not to mention all the other kind of things you could think about that would be fun on the moon. Think about amusement parks, or think about, if there's any golf fans here, think about an epic moon shot. It would take so long for that shot to land. You would just be able to hit that ball and just watch it soar for miles and miles, and it would probably go out of sight before it finally land, just because it travels so far in the air. So a lot of things that you might think that could happen on the moon. And although we always think about science when we think about the moon, it seems kind of inevitable that because there's a demand for it, everyone here raised their hand, or most people, I think everyone, anyways, because there's a demand for it, inevitably people will want to make that happen? Okay, so we only have a couple minutes left, so I'm going to try to finish off with a little bit of perspective. So it turns out that we've now come to the conclusion that there's still a lot that we don't know about the moon. And one of the biggest questions is, how did it get so big? When we look at the other terrestrial planets, so Mercury, Venus, Earth, and Mars, none of the other terrestrial bodies have a moon. Okay, so Mars technically has a moon, has two moons, Phobos and Deimos, but they're so small that you can't really see them. So this is the Earth and the moon to scale, and here's Mars's moons to scale. You can't see them. Here's the label. If you really squint your eyes, you can see just the label, but you can't see them. So Phobos and Deimos are 12 and 24 kilometers wide, respectively. So that's like driving from here to Etobicoke or here to Mississauga. You can't imagine ever living there or doing something substantial on there. But the moon is really substantial. The moon is huge. It turns out, maybe people don't know this, but the moon is actually bigger than Pluto. And so if the moon didn't orbit the Earth, but instead orbited around the sun, it probably would be considered a planet in its own right, which is something really interesting to think about, because Pluto used to be a planet. It's not anymore. Tier, hashtag tier. But yeah, so the moon, there's still a lot of things that we need to think about. And furthermore, we've also figured out that it's a very chaotic system. So if we turn back the clocks and redid it all again, would we end up with that same moon? Or would life be completely different? We don't know all the ramifications if there was no moon in that sky. And although we take it for granted day after day, it's currently sloshing the oceans, which maybe caused life, everything, all the nutrients to mix faster and everything like that. And so we don't even know all the significance of the moon, but one thing's for sure is that it's really important that it's there. And so in addition to not knowing all its secrets, we probably won't also get to know all the things about ourselves that the moon has witnessed. So as I said before, the building of the pyramids, the moon knows the answer to that, but we don't. Did the events in the Bible ever take place? The moon knows that, but we don't. And many other things. And so although we don't know a lot, in the end, we still don't know a lot about the moon. One thing that is for certain is that it definitely is a beautiful sight. Thank you.
We have a few minutes for Ari to answer some questions. If you'd like to put your hand up.
You were talking early on about the black volatiles.
Yeah.
You cited 11 point of water and 16 point of water, but that's at the standard atmospheric pressure. So I understand there's no atmosphere in the moon, therefore no atmospheric pressure. So wouldn't water just go away over time?
Yeah, so you're very correct. So it turns out that if the water is locked into the rocks, then it will stay there. And so there is still a little bit of water there today. If it's on the surface, then it will slowly eke away over time. But if it's locked in the rocks, then it will stay there. So for example, there's, water here on Earth is made of hydrogen and oxygen. And so if there's just free floating hydrogen, it would slowly escape into space as well. But because it's locked into water, then it stays there. So it turns out that the water that was part of the rocks, then once they got baked and cooked, then they turned into a gas. And then once they were a gas, it was on its own. Then you're right. Then it would go away. So that's why there's very little to essentially no water on the moon. Yeah.
Over here in the front.
You mentioned that the moon is gradually drifting away.
Yep.
And at a certain point, it will reach that tidal locking of both the Earth.
Yep.
But then I guess of course, the sun will probably be now the bigger concern, assuming that's not the issue. So if we put the sun out of the equation,
yep.
What would theoretically happen as if we
continue rolling the clock? That's a really good question. Yeah, so if we continue to roll the clock, first he's exactly right. The sun is probably going to go supernova or turn into a big supergiant in about 5 billion years. So trillion, we don't really have to worry about it even for future humans or whatever. But if we keep rolling that clock forward, it turns out that the lowest point, the point where it's the most happy, right now it's almost like there's a little friction between the Earth and the moon. They're like fighting a little bit. But when they're in finally perfect equilibrium is exactly when they're both tidally locked to each other. So once they're tidally locked, if we kept rolling the clock for another 100 trillion years, then as long as that system's, no huge comet comes and perturbs the system, as long as it just stays that perfect system, it shouldn't change anymore after that.
So no, the moon will not fly further?
No, it won't fly further away. That'll be the final point. Yeah.
Thank you.
Yep.
Maybe one more question?
I know vaguely that the moon contributes to the stability of the Earth. And without the moon, there perhaps would be no light.
Yeah, so...
I don't really touch, I know it's vaguely, but I would have liked to know it.
Yeah, sure. I'd love to give a comment about that. Yeah, so I didn't really talk about habitability and life in the moon. And so at the end of the day, this is my opinion because no one really knows because we're not there. So if there was no moon, how would that affect the habitability? So this gentleman is absolutely right that it does stabilize the Earth. And so if there wasn't the moon, then the Earth could vary wildly and it could rotate very substantially. And so that could create some very wild fluctuations and wild temperatures. But at the same time, we also see that life is very robust. So we see bacteria that can boil, that live in 100 degrees Celsius water, and also bacteria that live in Antarctica where it's really cold. So I would totally agree with you that, from my opinion, there would be no intelligent life, there'd be no humans, no dinosaurs, because we require more of a stable, constant climate. But as far as life in general goes, my guess is that it would still be around.
Okay, just before we thank our speaker again, I'd like to remind everyone that if you signed up for the 9 o'clock planetarium show, you need to go join Dana at the back now to head over. Otherwise, we encourage you to go over and visit the telescopes next door. I don't know if the sky's cleared up, but we will have demonstrations available. And if you've taken the time to fill up your feedback forms, we have cookies at the front. So let's thank our